So if you have managed to get into the Victor platform, if you can open the terminal, there should be a little icon that says terminal. And then all you need to do is type, oh, no, I'm not typing. Goldschmidt. And press enter. And it should.
Yeah, very good.
You should get this folder called Workshop Volatiles Goldschmidt 2026.
If you can't see what she types, I know it's tiny. Just the word Goldschmidt in the terminal, enter, and it will spin up this new folder that says workshops. Okay, so you won't be able to see, but hopefully you can all spell Goldschmidt or Google can help you.
And then if you go into there, that's where all our exercises are.
And then Harry, can we just make this really big?
Yep.
There we go. Yeah, that's a bit better. Okay. Okay, hands up once you get this folder open and you can see nice and high so you can see this. Okay, those who have not got that. Run around and see. Yeah, you have it.
Double thumbs up. Strongly work. It's science. Yeah.
Up and one of our Python experts will come to you. Who still needs help? Anyone? Yeah. Okay, everyone, we are going to open up this exercise 1.1. Okay, so this one here, so double click on it and it will appear on the right hand side. Hands up if you've never run a Jupyter notebook before. Okay, so the people next to you are going to help as well. But just quickly how it works is you have these things called markdown cells. These are just things that are text, so you don't have to do anything with them. And then you get to these grey boxes. These are called code cells. These are the things you're actually going to run. So what you do is you put your mouse in the code cell. Do you see I've selected this? Then you have a couple of options. You can press run here, the little play button. Or you can press Shift Enter if you're on Windows, or Command Enter if you're on Mac. Okay, so you would just press here. I'm going to press Shift Enter, and then it shows you a little star. That star tells you that the cell is running. And once a number has appeared, so here there's a tiny 1, that tells you the cell has run. Okay, so in this case, the first thing we've done is we've just imported the packages we need. So we need pandas, that helps you work with data structures, NumPy, which does the math, matplotlib, which does the plotting, and thermobar, which does the calculations we're going to be doing. So anytime you use a Python package, whether that's Volphi or SolveForX or thermobar, you should state the version that you used. So that's the next cell down. So again, just put your mouse in that cell, press run or press shift or command enter. And here this tells you using thermobar 1.0.72. Specifically, if you have an issue with any of these packages, that is the number you need to tell the developer. So if I've messed up, you tell me that thermobar version 72 is not working, and that will help me fix it. Okay, has everyone got to there? Hands up if you've got to here. Who needs help? Hands up if you need help. Okay, we're going to move on. Oh, Terry, do you need help? One sec. We'll just give people 1 minute to catch up. Don't stress, we're not going to be using pathlib today, so it's fine. Okay, so the first thing we're going to do is load in some data. So what this is doing, it is loading in an Excel spreadsheet. And this is basically a spreadsheet where one sheet, is melting fusion data and one sheet is matrix glass data. So just going to load this in using the pandas function to read in a data frame, basically. So for those of you who haven't done much Python before, I just want to show you what a data frame looks like. So here what we've said is we're loading in the melting fusion data as this variable data frame underscore melting fusion. So anytime in Python you want to inspect what you're looking at, you can do data frame underscore melting fusion, and you can see that we have all of these different columns. So silica, titanium, aluminum, etc., etc., and then the water and the CO2 content. That's what we're going to be using later in the exercise. Just as a little trick, if you're not sure what your columns are, you can always do dataframe.columns. And it will, oh no, it hasn't got that. There we go. This is the problem with doing it in front of everyone. There we go. There you can see the columns that you have if you want to go and look at it in more detail. Okay, so the first thing we're going to do is we're just going to make a simple plot. Oh, okay. What, sorry? How do I make a new line? Yeah, great question. So if you want to make a new code cell, you click this insert cell below button, okay? Yeah, great. If I do something without telling you, please feel free to stop me and interrupt. Okay, everyone got to here? Okay. The first thing we're going to do is make a plot. So we're using this matplotlib subplot command. This just makes a figure that is 4 inches by 4 inches. And the notation that we're going to be using is just this AX1. That tells us we're plotting on one axis, dot plot. And then basically the notation that we use is the name of the data frame, and then square brackets, and then the name of the column. So you can see that here, if you go data frame, melt inclusion, H2O, that will give you a list of the values in that column. So what we're doing here is we are just plotting H2O versus CO2. The OK tells us we want a circular symbol that is black. And then we are telling it we want the marker face color, so the color of the center, to be white. And we're labeling it as melt inclusion. Equally, we're going to plot the matrix glass. So that's just the second data frame. Columns are called the same thing. Only this time, XK tells us we're plotting with an X. And it's going to be black. Okay. The final two things we need for a plot are the X label and the Y label, and then just that we want a legend on. So hopefully you get a plot that looks something like this. Hands up if you've got this plot. Fabulous. Those of you who never Python before, you've all just made your first Python plot. Okay, what you'll notice is that these melting fusions have quite low water content, and that we thought for this eruption because they're kind of re-equilibrating in the conduit that's taking them down the rift zone. So we're just going to reset the water content to a higher value, just because that's based on previous data at Kilauea seems more reasonable. These have lost water towards the end. So we're just going to, here, that's what this cell is doing. We are just resetting the water to be 0.5. Okay, now we've got our data loaded in and we plotted it. The first thing we're going to do is calculate a temperature. That is because to use all these different volatile solubility models, they require you to know a temperature. So there's a variety of ways we can estimate temperatures for melting fusions. We can use just the liquid composition, or we can use the liquid and the olivine composition. So we're using this package thermobar, which does thermobarometry. So you can see here we're doing help and then tb.calculate lit only temperature. Anytime you do the help and the abbreviation for the package and the name of the function, it will give you the results for how you use that function. So you can see if you run this, it tells you you need to put in a liquid composition, an equation for temperature, and then it gives you the list of all the possible equations that you can use. So in this case, we're going to be using the Heltz-Thornburg thermometer. This was specifically calibrated for Kilauea. So we're using the MGO version of that because it was calibrated for this system. So how we do that is now we just need to rename our columns a little bit. And this is always the fun when you're swapping back and forth between Python packages. Thermobar requires you to tell it what phase your columns are. So SiO2 is ambiguous because thermobar can take minerals as well. So we just need to rename it as oxide underscore liquid. So that is what that first line of code is doing. It's just renaming the columns that need renaming. We're also calculating an FeO total column because, again, that's what thermobar requires as an input. And then once you've done that, you basically are using this function, calculate lick only temperature. You're telling it your liquid compositions, which is this new data frame we made up here with the renamed columns. And we're telling it a temperature, so we're going to use that Helsing-Thornberg thermometer. And then we're going to subtract minus 273.15 because all of these thermometers return in Kelvin because SI units are cool. Okay, then finally, we're going to insert a new column into our data frame. This basically says, if you do not have a temperature column already, now insert it using the temperature I calculated. Then finally, we're going to save this edited data frame that we've added a temperature to a CSV so that we can use it in the next notebook. So we're going to run this. It will now have generated a CSV, which will be in the output folder. So it's made your CSV in here. And then finally, we're going to plot it. So we're going to plot MgO versus temperature using a black outer circle and a blue inner. And you should be able to run that. And oh, look, it's a nice linear relationship between temperature. And this is because the Helsing-Thornberg equation we're using is actually very simple. It's 20.1 times MgO plus 1014. Okay, so the easiest thermometer in the world. I have it as a tattoo. No, I'm kidding. Right. Okay, so that is the end of calculating a temperature. It is now in our data frame, which we've saved to CSV, ready to load in. Has everyone got to here? Hands up if you haven't. Okay, yeah, John. Oh, you're good. Okay, should we move on to the next one, Erin? Any questions? Yeah, we've got a question.
Liz, keeping the original, if I close this picture all down, does it save my changes?
Yes. Yeah, it will save your most recent.
So if I mess this up,
You can re-download the folder. You can delete the whole folder.
Yeah, even if you mess this up, you're not going to mess this up. But if you were to, yeah, we're going to give you the answers. You might. We're going to give you the answers as well. So yeah.
picture.
Yeah. This is what Terry said your last time.
Do you want to do? I don't know what. You either talk all the way through it or just.
Sure. So we've done temperatures.
Yes.
Then okay. Okay. And how much? When does this end?
We'll run about.
Okay. So we're gonna. Yeah, we're gonna move on to the next notebook. So it's 1.1_2. So now it sounds like I was not listening because I was trying to do tech support, but it sounds like everyone's done, or whoever can, to run through the thermal exercises. You calculated temperatures for your sedimental conclusions. So now we have pressures and temperatures. So now we can start calculating the pressure vapor saturation. Vapor saturation. That's a word. Vapor saturation. Okay.
Yeah, it's pretty lame.
But I mean.
It's
fine, but I-
If you look at the actual term in like the surface which have water, the effect of multiplying by half weight and water, which is what Hawaii has, is smaller than the offset between the other thermometers. So I think it's still better to use a thermometer that's calibrated for the specific Hawaii melt composition.
Oh, yeah.
It's like 11 degrees difference between this and Tom Jay's thermometer. For another system, you have to want to use one with water, but this has done that for Hawaii. So great to have.
I'm just gonna sort of repeat that for folks online. So Tom Sisson asked of the thermometer that was chosen, it doesn't account for water. And Penny gave it a good explanation, better than I can give, but part of the point is that there's only 0.5 weight% in the Hawaiian conclusions that we're using. And so the difference that makes is sort of smaller than it sounds like the error between, or the uncertainties between the different models. So for this, we're going to go ahead and go with this, but definitely for other compositions, other more water-rich melt conclusions, you can choose from one of many models that are thermal bar.
Where I was like 200 models.
Yeah.
Yes,
Just in case you're interested, the models which do include water, I just looked up the coefficient. It's about 12 degrees per 1 weight% water. Okay, so you can have that in your head, and actually the offsets between models are about 20 to 30 degrees. So
Each is 100 degrees.
No.
Once you get really hydrous,
Okay.
it changes, yeah.
All right.
So 4% water.
So the second exercise here, again, we're calculating the saturation pressures. And all of these next notebooks are gonna follow kind of the same format. So we're just gonna start you off on this one with vesicle, and then you can go through the other ones. It'll be the same kind of process. So there's a little bit of primer here. We're gonna do the same thing we did before, right? So you wanna start by executing each cell as you go. So, and this is a normal warning that you get because on this on Victor, one of the models, which is the default model, is not included. And so this is just a warning telling you that you don't have that in your computer, but you can use all of the other models that are in Vesicle. How many people are familiar with Vesicle? Like half the people. So Vesicle is a water CO2 tool that just includes a bunch of existing models. So magmasat is a default. There's the Dixon. There's like basically volatile calc, something similar to volatile calc. There's Giacomo Marziano. There's Liu. So there's models that go from basalts, alkali basalts, silica-rich magmas. And it's essentially just a platform, one unified Python code so that you can access any of those models together. So sort of in the spirit of Victor. So we're going to be using a different model for this. Again, you can print the version, and this is Vesicle version 1.2.12. And then we're going to be importing that data again. And so this is going to be the same for all the notebooks. Just notice what we're importing here is a file that's in the output folder. But if you haven't run exercise 1.1, you can still run this. Just uncomment this line here, and it's going to pull from our folder called answers. So we've already pre-populated a folder with all of the files in it so that if you haven't run the others, you can still run this one. Okay. And then here you're sort of exploring the models, the different models that are available in Vesicle. So you can see all of them here. And we're going to be using the Giacomo Marziano model. Oh, that's the wrong number, but that's fine. And then really just rerunning all the calculations. And one of the things and you can go ahead and run through these if you're ahead of me. And you can move on to the other notebooks whenever you're ready. So one of the things that's really important about the work that we've done that you'll see later in the day and the work that is done to put these notebooks together is that each of these models take the inputs in a different form. And so the first step is really getting all of the input data into the right form to be adjusted by the models. And so that's written here. So this rename dict, right? Rename the samples, rename the columns in our pandas data frame, like your CSV file, basically. And then you can start running your result, running your calculation and getting your result. So here we just do calculate equilibrium fluid composition, put in the temperature, and then the model you want to use. You can uncomment this line to see what the resulting data look like. It's still running. So if it doesn't seem like it's doing anything and you see like a little asterisk here, that means it's still running. And if you get tired of waiting, you can try restarting your kernel. If anything, really, okay. Everybody get a Mac. If you want to do coding, get a Mac. I don't know what PowerShell is. Yes, so we put in okay, so all the Mac users go ahead and go to the other notebooks. The equilibrium fluid is calculating so all these models are water CO2 only. That's important to say. The other models that you'll see have sulfur included. But these act as sort of a benchmark for the underlying H2O CO2 models that are included in those sulfur-bearing models. So the equilibrium fluid calculation is doing the vapor melt equilibrium. So at whatever pressure and temperature and the composition that you have and the amount of volatiles that you have in your melt, it'll calculate the basically H2O CO2 ratio in the fluid at the point of vapor saturation. Or you can give it a different pressure and calculate it there, but otherwise it'll do it at the point of vapor saturation. So when you get the first infinitesimal amount of vapor, it's still going. So here's the results.
Water not changing.
So the water is not changing because we have prescribed 0.5, just 0.5 weight percent in the melt for all of the.
It should be.
Because we reset it in that first thing.
Sorry?
Because we reset it in that first thing.
Yeah. It's not calculated till you.
So it's not.
So we artificially reset water in these because we believe they don't go to diffuse loss, and that is why water is a constant line. So the CO2 is variable, but the water is not.
Yeah.
So.
Yeah.
How much more time?
I'll just quickly give Wolfie. I'll just quickly say about Wolfie and give people.
Okay. And then all the other models, like they have that.
So just to say, so like this was what the VCal example gives for water CO2. We've got the fluid inclusion. So I'm not going to go through it, but 1.3 is the same notebook, but using Wolfie. And Wolfie is not only has water and CO2, but also has sulfur in it. So if you have a sulfur content for your melt inclusion, you know it's FO2. If I just, for instance, I can, cancel if I do run. You can run exactly the same thing. It's going to take the same data that you used for the VCal calculations. And you can also choose lots of different model options. So like you had a Economarzano and Magmasat, etc. Wolfie has a bunch of models you can pick from too, which there's a bit of an explanation. And then it will run them all. This is giving you a warning because of the way we've defined the FO2 in this calculation, but it's still going to work. It's just going to assume delta FMQ. And then once it's finished running, you'll get a similar plot to before. So this is an example using a slightly different program to VCal to do the same calculation. I guess the key thing here is it's for each melt inclusion composition, we're calculating the pressure of vapor saturation and the fluid composition. Do you want to talk about fluid inclusion? I think.
So what part of the degassing happens?
Well, we're going to run that in exercise 2. The degassing parts are coming later. I reckon show fluid inclusions because it's a bit of a different one. So there you go. This is the output for Wolfie, for instance. So you can see we can calculate the pressure for each inclusion. And the diamonds are showing you what the fluid composition looks like. So we can see we've got the sulfur over CO2 plus sulfur ratio of the fluid inclusion for of the melt inclusion for each one.
Yeah.
I can come and help.
Square brackets. Yeah, I'll take it.
And then we're going to show, so those were both for melt inclusion data. So we're taking measured melt inclusion compositions and calculating the pressure of vapor saturation. But we also had to talk about fluid inclusions earlier. So Penny will just show a little bit about that.
At the back. She's using my Jupyter thing I spun up a few days ago. It might need spinning up again because I think because it's run, it's not working so well. Okay. Right, folks. So as I said in my little talk, we can also get pressures from fluid inclusions. So this data set you're working with is a melt inclusion data set I collected during my PhD. Charlotte
Dimitri, my postdoc, then came in and did fluid inclusions on exactly the same samples, including in some of the same crystals. So now we're going to calculate pressures using those just to compare. So the additional package that we need that we've not used so far is this package diadfit. That is a Python package that contains the equations of state that we need to calculate pressures from fluid inclusions. So we're just going to run that. We're then going to import the data. So this DF fluid inclusions, this is basically the supplemental information from Charlotte's paper. So if we just look at what that looks like, you can see there's a variety of columns. There's things like the Raman data, all of the dyad splittings, and then also the saturation pressures. And then there's also things like the CO2 density that we measured with Raman. There's a lot of columns there, so don't worry too much about looking through them all. So basically, for an equation of state, you have three variables: pressure, temperature, and CO2 density. And if you know two of them, you can solve for the third one. Okay, so in this case, we're going to be using this function calculate pressure for rho and T, because we're saying that the things we know are the CO2 density we measured, that's rho, and we estimate the temperature from the forced rate content of the olivine. So this basically, again, just tells you what you need. You need a CO2 density, a temperature, and then you can choose between two different pure CO2 equations of state. They're only about 1% difference, so don't worry about which one it's using. And then here, we're basically doing the calculations with the Sterner and Pitzer 1994 equation of state. So we're just going to do an example calculation to start with. So say you measured a fluid inclusion with a density of 0.1 gram per centimeter cubed, and you think it was trapped at 1300 degrees Celsius. You then obviously change this to Kelvin and run this, and it will tell you that that fluid was trapped at 0.31 kilobars. Just quickly, can someone change the temperature to 1100 and tell me what you get? So say we don't know our temperature to within 200 degrees. How much does that matter? 37, 37? 27. Okay, so 27 over 31, how big a difference is that? Not that big, right? So it's about 13%, but that is a huge error. Like, I like to think we know our temperatures in volcanic systems better than 200 degrees. You can see this really isn't that sensitive to temperature. Okay, so we've done that calculation for one fluid inclusion. We're now just going to load in the entire data frame of fluid inclusions. So all of the CO2 densities that were measured by Raman, all of the temperatures which were calculated from the forced rate content of the olivine, and then we're going to run that and save it to CSV. So you can just quickly see now we have this new results data frame called results PDF. And we can just plot a quick histogram with the pressures. So again, we're just using matplotlib, timesing it by 1,000 to get it into bars, because that's what all the solubility models are dealing with. And then we're just going to plot it quick. And you can see it's about 200 to 800 bars. So that is how simple fluid inclusion calculations are. There are some complexities. In reality, you would want to use a CO2 water equation of state. Again, we're not going to go into that in this workshop, but if you're interested, that's also available in diadfit. Come talk to me in one of the breaks about the problems with water in fluid inclusions. Any questions on that? Okay.
All questions.
Yeah.
Super simple question. What are the best fluid inclusions to use? Say you have an olivine or a quartz.
Yeah.
What kinds of fluid inclusions are the best to work with?
Yeah, so one of the big problems we have with fluid inclusions is they do re-equilibrate. So they basically really record the last place the magma was stored. So if you have storage at, say, 10 kilobars, and you bring it up to 5 kilobars, pretty quickly the fluid inclusions will stretch the olivine host and reset. The stretching rate, when you model it with olivine flow laws, is proportional to the size of the fluid inclusion. So the smaller the fluid inclusion, the more likely it is to retain high pressures. So really, if you're doing microthermometry, it's hard to measure anything smaller than 5 microns. With Raman, we can push down to about 1 to 2 microns. So I would generally just analyze a lot of them. If my big ones start recording lower densities, I'll then run fluid inclusion re-equilibration models, do EBSD, look at them. And in some really deep systems, it's the tiniest guys that are the hardest to analyze that are best. But normally we just start by like analyzing everything and then working out what has happened to them since they've been trapped. Just because the analyses take 4 minutes, so you might as well just analyze them and then see what you get out of it. Yeah, great question. Any other questions? Yeah.
I feel like I missed something, and I'm sure you have. So we know that there's fluid supersaturation. We're also calculating, assuming saturation with the solubility model. So I'm just a bit
Yeah, so I guess
as
it's
to that.
yeah, I think this is probably worth clarifying quickly. So the solubility model is obviously Penny knows this, but just for others, you are taking the amount of water and CO2 dissolved in the melt, along with the melt composition and a temperature, to calculate the pressure of vapor saturation. That is how a melt inclusion calculation works. A fluid inclusion calculation is totally different. We are saying the assumption is, at some point in the magmatic system, a fluid exsolves. That fluid has the pressure of the system at that time. That fluid then gets trapped within a growing crystal, and because it maintains its volume, that means it maintains its density, and then using equations of state, we can say, okay, its density is 0.7 gram per centimeter cubed now at room temperature. We would then say, hold on, so room temperature is 25 degrees in here, it's nice and toasty. We would say the pressure of the fluid inclusion today, if I were to bring it with me to Montreal, would be 4.2 MPa. That is based on its density, but we know that fluid was trapped at a higher temperature, in this case 1200. So if it was trapped at 1200, it's maintained its density, we can calculate the pressure at which it wasn't trapped, and the assumption is that pressure is the pressure that the magmatic system was at. Does that kind of answer your question?
Yes and no.
Okay.
I guess I'm saying there's excess fluid.
Yes, you have to be volatile saturated to use fluid inclusions. If you are not
actually volatile supersaturated.
Not necessarily.
Okay.
I mean, you have a fluid which you are trapping, and then you can talk about maybe the system was over pressurized, and that's what we're recording, and yet maybe it's 10 MPa too high or whatever. But yeah, this will not work if you work in Icelandic magmas, which is CO2 undersaturated. I can tell you from experience, you will not find any fluid inclusions, obviously. But yeah, generally, the more fluid we have around, the more fluid inclusions we find. Yeah, so they're quite rare. We find them in like between 1 in 10 and 1 in 1,000 crystals, depending on the samples we're looking at. Cool.
Good.
We can chat more in the break.
Should we go for the break?
Yeah, I think that's a break.
Cool.
I think people need a break.
Yeah, so there's a final notebook in there that I'll run and just leave up here. That just compares all our results, essentially. But we're now going to go to a break. We'll keep the 20 minutes or 15.
I'll say one comment.
Oh,
Here we go. Just like very quick comment. Sorry if you already covered this. These notebooks are not, you're not meant to leave here with the full understanding of how to do everything that we're giving you. We're trying to give you an overview, and this is why we sort of gave a couple of introductions and let you run with the other notebooks. These are there as a resource for you to be able to come back to later. So we're trying to give you a basic understanding, and you can come back to these anytime and run them and play with them. So keep that in mind. Don't feel like you're falling behind if you're like, this is too much and I'm not getting it. This is a lot. So I think everyone's doing pretty great. Thank you. Enjoy your break.
So back at 12:30.
Back at 11:30.